In this video, we'll be discussing the IoT connectivity technologies. So if you have not watched my previous video, we have discussed IEEE 802.15.4, Zigbee, Thread, ISA 100.11a, and wireless HART. In this video, we'll be discussing the other technologies. So the first one which we have is radio frequency identification device, or popularly known as RFID. So RFID enables wireless data capture and object categorization using RFID tags and RFID readers. So unlike barcodes, RFID does not require line of sight, making it more versatile in various applications. We'll understand the key components one by one. So the first one we have is RFID tags. So RFID tags will have an integrated circuit IC and an antenna enclosed in the protected casing. So inside the tag only there will be a circuit IC, and along with that there will be an antenna also to wirelessly transfer the data or message. So speaking of the tags, there are again two types of tags here. First one is passive tags. So passive tags are powered by RFID reader. So they are cost effective. Speaking of active tags, they are equipped with their own power source for extended range and functionality. Passive tags means it can perform only read operation, whereas active tags you can read and write. Both operations can be done here. So RFID reader or interrogator. So RFID reader will read the data from the tags via radio waves. So we make use of radio waves to transfer the data from the source or the tag to the host system. That is by making use of this RFID reader. Then we have antenna, which will facilitate the communication between the tag and the reader. So here we have the diagram. So speaking of this diagram, first step, RFID reader will emit radio waves to detect the power tags. So after that, tags respond by transmitting their encoded data back to the reader. So after this, reader will convert radio signals into digital data, radio to digital data for processing. Now the data is sent via a host system. Host system here can be internet, or it could be Ethernet or Wi-Fi, and it is further updated in the database. So that's how RFID works. So I've written down all the steps here. Moving on further, speaking of the applications. So if we take applications, first one is inventory management. So here it enables real-time tracking of the stocks and all. Then it also ensures accuracy by automatically logging products entering and exiting the storage. So there we can make use of RFID standard. Then we have asset tracking. Asset tracking in that it locates and monitors valuable assets in industries, warehouses, or healthcare, and it also improves the efficiency by reducing the search time, and any misplacement is happening, that will be taken care of it. Then we have personal tracking. Personal tracking, it is used in organizations for attendance systems and access control. You must have seen in colleges, right? So yeah, then it ensures security by logging personal movement in sensitive areas. Then last one we have a supply chain. So it will keep a track of goods across the logistics and distribution networks. It will make sure that there is smooth flow of products with minimum manual intervention. So ultimately, to conclude RFID, we can say that it has ability to automatically capture the data, and it has high reliability and speed, making it very useful in logistics, retail, and manufacturing industries. Next one we have is NFC. NFC, or near field communication. So NFC was jointly developed by Philips and Sony as short-range wireless connectivity standard, enabling peer-to-peer communication or data exchange between the compatible devices which are present in the close proximity, that is within few centimeters only. Let's see how NFC works. So communication between NFCs is achieved by principle of magnetic induction. So whenever the devices are brought close to each other. So NFCs can be used with other wireless network technologies such as Wi-Fi after establishing and configuring the peer-to-peer networks. So the typical NFC operating frequency is 13.56 megahertz frequency, and the data rate supported here is 106, 212, or 424 kilobits per second, making the communication very fast and reliable or efficient. Speaking of, let's see how it works. So a small electric current is emitted by NFC reader, which creates a magnetic field that acts as a bridge in the physical space between two NFC devices. Further, the generated electromagnetic field is converted back into electric impulse through another coil on the client's device. So data such as identifiers, messages, currency, status, and others can be transmitted using NFCs. Example of this RFID can be the when you charge the metro online. When you charge the metro card online, you have to get into the station and punch it there, or update the if you have recharged, like suppose 100 rupees, if you have recharged to metro card, you have to go there physically and put your card there into the reader, and then upgrade the balance, right? So you must have seen this in Bangalore metro. So that is one of the easy examples to remember for RFID tags and RFID readers. Speaking of NFC, NFC is the metro like metro card which you have. When you press the metro card on the gates, it will automatically open, right? So that is one of the examples for NFC. So we were here, data such as identifiers, control can be transmitted using NFCs. So some of the most commonly used NFC platform are smartphones. Smartphones again used for payment purpose, and then we have card readers, again metro card readers, commercial touch payment terminals. So yeah, this is, then we have a figure here which is the outline of NFC operation. And yeah, speaking of the communication and all, first one we have is passive devices. Passive NFC devices example is credit card. So here credit card is used for secure contactless payments. And we have tags here. Tags are small low cost passive devices which are used for basic data storage. They can be seen in marketing or inventory systems. So from there, on the other side, we have active devices. In that we have smartphones. Smartphones serve the versatile NFC devices. So it supports payments, data transfer, pairing of two devices and all happens through smartphones. Then we have NFC reader. So this is a central device which interacts between the NFC devices along with the local network. Okay. Speaking of the local network will facilitate maintenance, management, or local communication. Then we have public network here. Public network is used for connecting to broader systems like public transport or finance or utility bills. Then we have secure database here. Secure database is like a central storage which will store to say sensitive information. For example, the identification data, when did you log in, log out in the metro, all that would be stored here. So NFC devices can be grouped into two types, passive and active. Passive devices cannot process the information. They simply store the information which is read by the NFC reader. Active devices can communicate with active as well as passive. So active devices are capable of reading as well as writing data to other NFC terminals. NFC currently supports three information exchange models. So the first one we have is peer-to-peer. It is most commonly used in NFC modes. It enables two NFC devices to exchange info. In peer-to-peer mode, the transmitting devices goes active because it is sending the data, and receiving devices will become passive because it is receiving the data. Then we have read-write mode. This mode of information exchange allows only one-way data transmission. Only one person will send and the other person has to receive. Whereas in peer-to-peer, this can send, here it can send, and here also it can send, but for one instance, even when this sends, on the other instance this can send back. Whereas in read write mode, it is one way communication happening. NFC device connects to passive NFC device to read the information from it. Then we have card emulation mode. It enables NFC device, generally smartphones, to act as contactless credit card and makes payment just by a single tap on the NFC reader. I guess we have all made use of this feature in our cards or mobiles, right? So this was about the NFC devices. Speaking of applications, let me write down the applications here. First one we have is payments. So by tapping a smartphone or an NFC card on the reader, you can make quick payments. This feature is utilized in credit cards, digital wallets, secure payment platforms. Then we have public transport. So in public transport, the bus pass or tickets are stored in NFC cards. They will enable access with a simple tap. Even our bus pass which we have in our BMTC again makes use of NFC. There's a chip present inside it, right? So then we have utilities and maintenance. So it simplifies maintenance logs and utility bill payment. Then the most important, data sharing happens. So peer-to-peer file sharing between the smartphones without manual setup or pairing can be done through NFC. So this was all about NFC. Let's move further. We have ultimately we can say that NFC provides versatility, it is very speed, and there is secure communication which is happening between various devices. And NFC can be seen in modern smart devices these days, and it is like a foundation for the upcoming technologies. Then we have DASH7 here. DASH7 is a wireless communication protocol that is derived from active RFID standards. So this is again a subchain or a substitute or a child from the RFID family or RFID standard. It operates on 433 megahertz frequency band and is widely adopted in diverse applications including the agriculture, vehicles, consumer electronics and mobile devices. So Dash7 is unique for its support for NFC compatibility and its adaptability to IoT communication systems. In NFC, we had read that it supports other technologies also, right? So this is one of the examples. Dash7 is compatible with the NFC technology. Looking at the key features, first one we have is frequency and modulation. We can say that it operates on 433.92 megahertz using frequency shift keying modulation for reliable message transfer. Then speaking of the compatibility, Dash7's 433 megahertz frequency interacts with NFC's 13.56 megahertz band. So we can say that this compatibility is happening between NFC and the Dash. And this will make sure that there is higher order harmonics happening, right? Then we have OSI protocol stack. So Dash7 has a fully defined OSI compliant protocol stack enabling compatibility with technologies like Sigfox, local range. It integrates a file system making it suitable for low cost processing systems. Then we have speaking about the power consumption. It supports low power, low memory, tag to tag communication, enhancing dense deployment or network deployments. Speaking of the rate and latency, effective communication range is between 1 to 100 kilometers, 10 kilometers, and querying latency is 1 to 10 seconds. That is, it means it is in the medium range of latency. Looking at this device, looking at this figure, which speaks of the Dash communication architecture. First one we have is the smart devices. Smart devices are the user devices that can communicate with Dash7 gateway. Examples could be mobiles or the IoT sensors which we have, or it can be any wearable devices also. So this was about the smart devices. Then on the other hand, we have tags. So tags are the active RFID tags that transmit the information over Dash7 network. So these are used in asset tracking, agriculture, inventory management, and so on. Then we have NFC readers. NFC readers are the Dash network will make sure or will enable communication with NFC devices by utilizing harmonic frequencies. So this will allow seamless integration between the NFC and the Dash7. Then we have gateways. Gateways are they are used to connect Dash7 devices to internet by making sure that there is like proper flow between the local and the global systems, and consistent data flow is happening. Then we have internet. Internet provides access to cloud-based applications and storage for Dash7 enabled devices. Next we have, yeah, speaking of applications, one we have is agriculture. So in agriculture, Dash7 will help us monitor the environmental conditions and asset tracking in the farms. Then we have consumer electronics. So it will enable communication between the devices in smart homes or the consumer gadgets. Then we have vehicles. So they are used in fleet management, vehicle monitoring and logistics. Then we have IoT systems. So Dash7 acts as a bridge between the NFC and IoT, enabling seamless communication between the devices. Looking at the figure here, we have Dash7 stack compared to the OSI stack. So if you see here, we have application layer. In application layer, it manages user applications and services like device querying and data processing. Then we have presentation and session layer. In this, it will enable data formatting and session management between the devices for making sure that there is secure and reliable communication happening. Then we have transport layer. A transport layer, it handles the end-to-end delivery of data. Then in network layer, we have routing and device addressing, protocol adaptations to technologies like Sigfox and LORA are all taken care in the network layer services. Then we have data link layer. In data link layer, it provides logical link control LLC and media access control MAC, ensuring that collision-free data transmission is happening. Physical layer means we know like physically it will make use of FSK modulation for data transmission over wireless channels. So here I've written down all the points. Moving on further, yeah, this was all about Dash 7. Ultimately, we can say that Dash 7 stands out as a versatile protocol. It has low power, low range communication, and key concept is that it will help us to connect other technologies. RFID, NFC integration can happen here easily. Its robust architecture will make sure that the compatibility and evolving technologies can be addressed easily. Then further we have Z-Wave. Z-Wave is a wireless communication protocol designed for home automation, offering a simple and more economical alternative to Zigbee. Compared to Zigbee, this is better. Let's see how it's better. So it consumes less power than Wi-Fi, has a greater range than Bluetooth, and supports a variety of devices including sensors, locks, applications, power distribution systems. So let's look into the key features of Z-Wave. First one we have is the frequency and modulation. So it operates on 800 to 900 megahertz frequency range. That is, it will avoid interference from Wi-Fi and other devices like 2.4 gigahertz devices. 2.4 gigahertz frequency is seen in IEEE, the first one, the first technology which we have studied, right? So here it uses a Gaussian frequency shift keying, GFSK modulation with pulse shaping, which limits the bandwidth and reduces the signal interference. Then we have encoding. So it implements Manchester encoding, which is a method where data bits are represented with a transition into signal. So this is done to ensure that there is accurate timing and synchronization happening while the data is being transferred. Speaking of the topology, we can say that it employs source rooted mesh network topology. And mesh topology healing messages enable the network to bypass radio dead spots. So next we have the central controller, that is each Z-Wave network has one central controller or hub that manages the devices. Then the hub connects to internet and it will enable remote monitoring and control. We can say that Z-Wave supports older devices and ensuring compatibility with earlier versions of protocols. A single Z-Wave can manage up to 232 devices. This is one of the major advantages of Z-Wave over Zigbee, all identified by unique node IDs. Then we can say that only static devices are included in the network. One more point, let me add it down here. Only static devices are including in network, excluding the mobile devices to maintain stability. Speaking about this figure 7.16, Z-Wave deployment and communication architecture. First we have is the Z-Wave controller. So Z-Wave controller will act as a central hub and it will manage the communication with all Z-Wave devices in the home network. Assuming this as a home network, and all these are the devices, Z-Wave controller will act as a central hub. So this Z-Wave, no, it is connected to internet to allow remote access and control. Then we have Z-Wave devices. All these are Z-Wave devices. It can be sensors, smart locks, and any other thing. So each device will have unique ID, unique node ID. That's what we can see here. Then all these are connected in mesh topology, right? So messages from devices outside the hub's range are routed through intermediate devices or intermediate nodes. For example, a device in room A can communicate with the hub via another device in room B. Then we have network IDs and isolation. So each logical Z-Wave will have a unique home ID, and devices with different home IDs cannot communicate. That is, here we are ensuring privacy and isolation. So if this has to communicate, it has to go through the gateways only. So this was about the figure. We have discussed all the key points. Next we have is a Z-Wave protocol stack. So looking at this figure here, we can say that at application layer, it handles smart home functions like turning the lights on or energy management and so on. Next, speaking of the security layer, here it will manage encryption and secure communication. Then we have network layer. In network layer, source routing is happening where the message path is determined by the sender. Then we have transport layer. It ensures data reliability with acknowledgement and retransmission mechanisms. Speaking of physical layer, GFSK modulation and Manchester encoding is done here. That's what I've written down here. Moving on to the applications. First one is home automation. Home automation means smart lights and power management, thermostats, etc. Speaking of security systems, smart locks, motion detectors, surveillance cameras, and so on. Energy efficiency, that is, it monitors and controls home energy usage. And then we have elder care to track the activities and provides automated assistance. So this was all about the Z-Wave. Ultimately, we can say that Z-Wave is best for stable and efficient home automation. It ensures compatibility and it is very easy to use, and reliable data transfer is also happening in Z-Wave. Moving on further, the next technology which we have is weightless. Weightless is a low power wide range area network LPWAN standard which is designed for IoT applications that prioritize low power consumption, low data throughput, and moderate to high latency tolerance. It operates in sub gigahertz frequency bands, that is 138 megahertz to 923 megahertz, and supports both licensed and unlicensed ISM bands, and it enables long range cost effective communication. Looking at the key features, first one we have is the frequency bands. Here we have the standards. Frequency bands means it frequency bands only, it operates in sub gigahertz frequency, that is we have discussed here, and these frequencies are often exempt from licensing, reducing the deployment cost. Speaking of the standards, there are three standards. Weightless P means it is bidirectional communication, so it supports licensed and unlicensed bands. So this weightless P is widely used. Mostly this is only used. Okay. Then we have weightless N. Weightless N is uplink only communication for applications like telemetry. Then we have weightless W, which is used for TV white space frequencies for communication, but has limited adaptation. Compared to these three, weightless P is widely used. Speaking of the network design, we have star topology where the end devices can communicate directly with the base stations. Then we have base station network. So base station coordinates communication within its cell and connects to base station network for broader management. Then we have low power and low complexity. So end devices are low cost and consume less power. Typically, it is very less, 0.003 mega millihertz, milliwatts, and all. Okay, and base stations transmit at high power rate to cover larger areas. Speaking of the message transmissions, it supports bidirectional communication with acknowledgement. If acknowledgement is there, it speaks about reliability. Then we have what do we have? Then we have payload scale, payload size. So it is designed for small payloads for less than 48 bytes. It is ideal for IoT use cases like sensors and actuators. Here we have discussed all the key features. Let's look into the figure now. So 7.18 typical components of weightless standard and its protocols. So the first one we have is end devices. End devices form the leaf nodes in the network. They represent IoT devices like sensors or trackers. They operate at low complexity and power, and yeah, they save energy. That's it. Then we have base stations. Base stations serve as a central coordinating node for each cell present in the network. Right. Then we have base station network. Base station network will manage multiple base stations within that network. It will provide authentication, resource allocation, and scheduling. Then we have protocol layers. We have weightless MAC and weightless PHY. So these two protocols are there. Medium access control layer to manage the radio source scheduling and efficient data transfer, and weightless physical layer which includes modulation and data framing. Then we have data transmission. So data transmission flow, here the data from application layer will pass through the weightless interface. So it prepares it for transmission over the MAC and PHY layers. So acknowledgement frames are ensured for reliable message transfer. So that's how this entire our entire components and protocols work in weightless standard. Moving on further, we have applications. So first one is industrial IoT. So it is used for monitoring, controlling machines in factories. Speaking of smart agriculture, again soil monitoring, irrigation management, and all. Then we have asset tracking. Asset tracking is to manage the logistics, supply chain operations, and so on. Utility monitoring, like smart meters for water, electricity, and so on. Then we have environmental monitoring, that is to check the air quality, weather condition by sensors. So this was all about our weightless standard. So here we have covered all the major points. Weightless standard is very suitable because it is cost sensitive. Firstly, it has low complexity IoT deployment, and it has bidirectional communication and low power consumption, and it is very flexible. So these are the key points or takeaways from weightless standard. So here we have tried covering 4 to 5 technologies. If you have any doubts, do let me know in the comments. Rest of the technologies would be covered in the upcoming videos. If you have any doubts, do let me know in the comments and subscribe to my channel. Stay tuned and yeah, thank you.